Lots going on in the southern Indian Ocean as Ocean Infinity wraps up week 3 of the current phase of the seabed search for MH370. Today is Tuesday, January 20th, 2026, and the survey vessel Armada 8605 has been deploying all 3 of its AUVs, but suffered a setback as weather on the open ocean grew fierce. Fortunately, we have a detailed report explaining what the ship's been up to, courtesy of the Malaysian government. I'll break that down for you. I've also got an eye-opening conversation with a veteran NASA scientist. That's all coming up right now. Hi, everybody. Jeff Wise back with you with another episode of Finding MH370, the podcast where we dive deep into the full range of technical evidence in order to solve aviation's greatest mystery. Last week, you'll remember, we expected that the scan of the seabed was about to end. Ocean Infinity's research ship Armada 8605 was scheduled to return to port the very next day. Well, soon after that episode dropped, Ocean Infinity changed their plan. The Fremantle port management system showed that the arrival date was changed from January 20th to January 29th, so more than an extra week. That was definitely a welcome change, as it's always a good thing if Ocean Infinity is going to spend time out on station scanning the seabed. Unfortunately, the weather did not play along. A storm hit the area. Armada 8605 was forced to retrieve the AUVs and wait out the strong winds and the massive waves. Now, usually we have to deduce this kind of thing from the movement of the ship on marine tracking websites, but on Monday, the Malaysian government took the unusual step of releasing an update, basically summarizing what Ocean Infinity had been up to. The statement was released on the MH370 family's Facebook page. It reads like this, quote, "Between 06 and 15 January 2026, search operations aboard Armada 8605 were conducted in the designated search area on the southern side of the 7th Arc, primarily utilizing up to 3 Hugin autonomous underwater vehicles, AUVs. Operations resumed on 06 January following prior activities and proceeded steadily through the reporting period, subject to technical and environmental conditions. From 06 to 14 January, search activities were largely uninterrupted. The AUVs were deployed on planned missions, regularly monitored by the vessel and recovered as required for data download, battery replacement, and preparation for subsequent launches. A brief technical issue on 7 January required the early recovery of 1 AUV. However, this did not significantly impact overall progress, and full 3 AUV operations resumed thereafter. Intermittent handshakes were observed during several missions, but did not impede data acquisition or mission continuity." Okay, and aside, what I take this to mean is that at times the ship had trouble communicating with the AUVs as they were on their mission. That could be potentially worrying, since it could conceivably lead to the AUVs getting lost, but apparently it all worked out. Okay, let me continue with this report. On 12th January, all 3 AUVs completed their respective missions and were sequentially recovered to enable data handling and redeployment, ensuring continuity of survey coverage. Weather conditions remained favorable for operations until 14 January, allowing sustained surveying efforts. On 15 January 2026, search operations were halted due to inclement weather, and all 3 Hugin AUVs were safely recovered aboard Armada 8605. Operations are planned to resume once conditions improve and it is deemed safe to do so. Okay. Last week's episode dropped on Tuesday, January 13th. That means that they had only another day and maybe a bit more to search before the bad weather came in. So let's look at the progress that they made. Here's what they searched as of the 13th. And here's what they searched as of a week later on the 20th. As you can see, not a lot of progress. At the end, you see the track here in red. That means that they're moving slowly and they're wandering from the search area. Probably what's happening is the ship is just trying to keep the bow pointing into the waves trying to endure the ups and downs of the waves as best they can. Probably not a lot of fun to be out there right now. Kevin Rupp reports on Twitter that they've had to deal with waves as high as 5.7 meters. That's 18.7 feet. Yikes. So, what lies ahead? Their current plan is to leave the search area on the 24th local time. That's 3 days from now, in order to get to port at Fremantle on the 29th. A quick look at windy.com. Here's the outlook for Wednesday. Winds up to 30 miles per hour. That's pretty sporty. Here's Thursday, winds around 20 miles per hour. That's not so bad. And here's Friday, looking even more relaxed with winds of just 11 miles per hour at midday. Now, bear in mind that wind speed does not necessarily translate directly into wave height, but it does seem like things are trending in the right direction. So hopefully they'll be able to get those AUVs out for a while before they have to pack up and head back to Fremantle. I should add that Kevin Rupp is less optimistic. He wrote on Twitter earlier today, quote, "After a brief respite, conditions are about to get pretty rough for Armada 8605 again. I still don't know why they didn't run for Fremantle," end quote. So Kevin clearly doubts that they're going to get any more scanning done in this phase of the search. It seems like that extra week that they added was what we would call a long walk for a short drink. We'll have to wait and see how it pans out. I'll have more for you about that in the next episode. As ever, if you want to get a free email when the episode drops, you can sign up for that at findingmh370.com, the show page. Okay, now another interesting piece of information from the Malaysian government's update was this table showing how much of the seabed they've been able to scan each day before the bad weather hit. Between January 6th and 15th, they had the AUVs out for 10 days, and they scanned between 30 and 870 square kilometers per day. In total, they added 4,336 square kilometers to the previous total of 2,900 square kilometers for a total of 7,236.4 square kilometers. That is about half of the 15,000 square kilometers that they plan to search. But here's an interesting thing that one of the viewers at Glenn354023 pointed out. In the second column of the table, you can see the daily line distance that the AUVs carried out each day. So I interpret that to mean that's how far the AUVs traveled over the seabed as they sent out their side scan sonar beams. Well, if you divide that figure into the total searched on that day, you get the width of the area scanned. Glenn writes, quote, "By this math, they are saying that they are covering 1.8 kilometers in a single pass, 900 meters per side of the vehicle. The stated range of the high SAS is 260 meters max. How are they outperforming the specs of the equipment by a factor of 3? It's a valid question to be asked," end quote. I agree. I think this is interesting. Maybe the explanation is that the line range is how far each of the AUVs traveled, not all of them collectively. So that's why they're multiplying by 3, because 3 AUVs together can get that width. Or maybe they have some new technology that lets them scan 3 times further. I think that the former is more likely than the latter, but if anyone out there has some insight from the company, do hit me up. Okay, that's the status of the search right now. For the rest of the episode, I want to pull back the lens, as it were, and talk about a subject that doesn't get a lot of attention, but I think is important. Namely, what is the proper way to investigate a mystery like this? Now, we're all hoping that the seabed search is successful, but if it isn't, then I feel like it's going to be incumbent on us to ask why and what happens next. Already, Australia has thrown in the towel on the attempt to explain what happened to MH370. And apart from allowing Ocean Infinity to do its search, Malaysia has thrown in the towel as well. Really, it's not too far off the mark to say that investigators have simply given up and gone home. And I don't think this is an acceptable state of affairs. This is not how the most important aviation mystery of the modern era deserves to be treated. So, how should a very, very important investigation be handled? I wanted to talk to someone who would know firsthand. So I reached out to Dr. Nigel Packham, who spent decades at NASA studying safety and risk in manned spaceflight and was involved in the investigation into the Space Shuttle Columbia disaster. NASA spared no expense to make sure that it understood exactly what went wrong so that it could make sure that it didn't happen again. It had an attitude of full commitment, no excuses. I think that MH370 deserves that as well. It was a real honor to have Dr. Packham on the show. Dr. Nigel Packham, thank you so much for taking the time to talk to me with me today.
You're very welcome, Jeff. It's a topic I'm always very happy to talk about.
So you recently retired from NASA, where you were the Associate Director of Safety and Mission Assurance at the Johnson Space Center in Houston for many years. One of your high-profile roles was as project manager for the team that investigated crew survivability for the disaster that occurred on February 1st, 2003, when the Space Shuttle Columbia disintegrated during re-entry. The 7 astronauts aboard died, and the accident led to the termination of the Space Shuttle program. The investigation into what happened and what to learn from the disaster was a major effort that involved a lot of money and expertise. It was clearly a priority for the U.S. government. I think it can stand as a model for what a thorough investigation can be, really in contrast to MH370, which of course was never solved, and the investigation has been set aside by the governments responsible. You were not part of the main investigation per se, but you led a separate team that looked at a lot of the same evidence, I imagine, but with a different goal. I was hoping you could explain about what that goal was.
Of course, Jeff. And let me just say that Columbia didn't actually result in the ending of the Space Shuttle program.
Okay.
It put it on hold for a couple of years, just as it did after the Challenger accident, so that the team could investigate the accident first of all, and we'll get into that in a second.
Okay.
Also make any changes that were necessary to ensure that future flights could be as safe as they could possibly be. So the main team that was involved in investigating the accident, which was called the Columbia Accident Investigation Board, which was chaired by retired Admiral Gaiman, their primary job was to find out what the cause of the accident was. And they did that very efficiently. They were stood up on the day of the accident, and they spent 8 months investigating it and came up with multiple recommendations for the agency to implement for a return to flight. As part of that, the agency also discussed looking at the survivability of that accident and wanted to focus in on what could we do to improve survivability for future accidents if they were to occur. So that was why the team that was formed, which was officially called the Spacecraft Crew Survival Integrated Investigation Team. But it was a very small team that I was privileged to lead from about the 2006 timeframe on to its conclusion when the report was published in 2008. And its focus was to actually build upon what the Accident Investigation Board had found, but to drive more into what aspects of the accident could be evaluated for improvement in survivability for future accidents.
Okay. And when the flight had launched on January 16th, and as it was taking off, a piece of foam came off part of the structure and hit one of the wings and dislodged some of the thermal tile there. Is that right?
So you're exactly correct. 81.7 seconds to be exact into the flight, a piece of foam about the size of a small suitcase was liberated from the very large external tank, that orange external tank that sits that the shuttle actually sits on for ascent. and struck the leading edge of the left wing. Now, an important differentiation here is that the left wing is not covered in tile. The wings themselves are not covered in tile. They're covered in a material called reinforced carbon-carbon.
Okay.
So they are thermally protective, obviously, but the main body of the shuttle is covered in silica-based tile.
Okay.
But the leading edges of the wings, because of the intense heat that they see, are actually covered in reinforced carbon-carbon,
Okay.
which unfortunately, even though they're very, very thermally protective, are also very brittle. So the foam strike that occurred about 81.7 seconds into the flight essentially created about a 2-foot hole in the leading edge of the left wing, which was not known, of course, until an investigation was completed.
Okay, so this is where I guess I had a misconception when you and I were talking about this earlier. I was under the impression that engineers on the ground knew that this had happened. That is not the case. You're saying that this was not known at the
Well,
time.
there were multiple engineers, and I would say a small cadre of engineers that truly believed that, I mean, there was no doubt that an impact had occurred, as has happened and had happened on multiple previous flights. But most of those impacts had occurred at a point in the ascent where the damage would have been minimal because of the accelerations and the specific pressures involved. But there was a small cadre of engineers that believed that because of the location of the strike, that some damage had occurred to the vehicle. However, there was no evidence at all during the flight that came to light that showed conclusively that there was damage to the left wing.
Okay. Now, obviously, the way things panned out, it turned out that, of course, there was that damage. In retrospect, should it have been carried out? Should they have done something different? Should they have treated the evidence differently?
Well, again, the agency has, during the flight, we have what is called a mission management team. And that is composed of senior level managers chaired by an individual that basically every day during the mission meets and discusses events that have happened, including post-launch and preparation for entry. They determined, based upon the information that they were given at the time, that there was no threat to the vehicle upon entry. And of course, the only threat to the vehicle came upon the deorbit burn actually happening and Columbia coming out of orbit and going through the atmospheric entry heating that every shuttle had endured. But because of the hole in the left wing, that created a pathway for hot plasma to enter, and then the rest of the events that unfolded that day, including the disintegration of the vehicle over the skies of Texas. I would say that there were efforts made during the flight to press for imagery of the vehicle on orbit. Those efforts did not come to fruition for reasons I won't go into, but and it would have been very simple to have seen it using assets, for example, from the Department of Defense. It would have been very obvious that there would have been a hole in the left wing. Now, I should say that the crew were aware of the strike. They were told about the strike. But there's nothing that the crew could have seen or done on orbit to actually have verified that that hole was there or not.
They could have gone like on a spacewalk to look at it or fix it. No.
Well, first of all, they couldn't see it because of the way that the left wing is actually, once the payload bay's doors are opened, the views from the flight deck or the aft flight deck looking aft towards the tail of a shuttle and towards the wing, the left wing was obscured by the payload bay doors. So there's nothing they could have done to see it. They also did not have a robotic arm on that particular flight because of the nature of the flight, which I'm sure we'll get into in a second.
Yeah.
So the robotic arm that was almost always present on flights could not have gone over and looked underneath the payload bay door and seen the image to the left wing.
So as you were saying, on reentry, the hot gases essentially melted the wing, and which led to the shuttle losing control, disintegrating. Your job was, with your team, was to understand what the effect of all of that had on the human body, whether it would have been. And I want to ask you about that stuff a little bit later, but for the purposes, I think, of the listeners and viewers who are, looking at this through the lens of MH370, how does one conduct an investigation in a fruitful way?
Sure.
And I think you were very successful in that. And so I wanted to ask you, for instance, when you and your team was looking at a very large amount of evidence, and you're trying to piece it together, you're probably playing with different ideas. What was the sequence of events? What caused what? Did you find that there are differences of opinion? I guess I want to ask you, because I think one of the really hard parts of doing science is resolving different points of view, different perspectives. Is that something that cropped up?
Absolutely. And because of the nature of the accident, it involved a huge number of different entities from different areas of expertise, right?
Mm-hmm.
Aerothermal engineering, mechanical engineering, electrical engineering, coupled with the pathology from the autopsies of the crew members, right? So to put all of this vast amount of data together took a very large number of people to start with in the investigation of crew survivability, which whittled down to a crew of about 10 people in the end that put the report together. But originally, the vast amount of data that the orbiter generated in real time and was beamed down to the ground from telemetry from the satellites on orbit, coupled with a lot of the data from the debris, video evidence that was received from the general public and from the news media. So all of these entities had to be put together, collecting all of this data. And the first thing we did, and you're quite right, is to put a timeline together of exactly what happened all the way from the time that the shuttle did its deorbit burn to drop it out of orbit, all the way through from atmospheric reentry, where the hot gases, as you said, entered through that hole in the left wing, creating multiple issues, which were seen on the ground, even through telemetry. And the first indication of a problem, for example, was an indicator of a tire pressure sensor that had gone off scale high, and that was relayed to the ground. And that was the first indication seen in the flight control room that a problem was starting to evolve. But yes, the timeline was extremely important for us. And that putting that timeline together took a very large amount of time.
Now, that's interesting. You're talking about the different kinds of expertise that have to be brought together. Something very similar with MH370, where we have really radically different kinds of evidence. It's almost like that famous story about the three blind men and the elephant. Everyone is touching on a different aspect of the case and might come away with a very different overall impression. The goal, you're the team project leader. You have to kind of help integrate all of these different perspectives into one coherent understanding.
Sure.
I wanted to see if you could talk about because I think it's natural as you try to understand something, you come up with different possible ideas. And some of them might turn out to be wrong. How do you integrate? How do you sort of carry along these different? They can't all be right, but you have to carry them together and resolve them. How do you do that?
Absolutely. So my job as a project manager was to lead the team through a lot of those discussions, right?
Mm-hmm.
I'm not a tech. My expertise is in the area of life support systems. So I spent a decade more than a decade studying and keeping abreast of the life support systems on the shuttle, space station, those needed for Mars and the moon, for example. So my area of expertise really didn't come into play except as a leader of the team.
Mm-hmm.
So this team, which was comprised of different individuals, right? Some who have very strong feelings and strong emotions and strong convictions that certain things happened a certain
Mm.
way and in a certain sequence. My job was to keep the team concentrating on the data. What did the data tell us?
Mm.
And in some cases, the data was certain, absolutely certain, in which case we could say this event happened at exactly this time and in exactly
Right.
this manner. But then we got into what I would call the spectrum of possibilities. Right?
Mm.
So there's this certainty on one end, which is based upon absolute factual data, but on the other end of the spectrum, you have it may be possible. So this explanation may be possible, but there may be other explanations that might also be explained by the data that we have. So my job in that respect was to guide the team into understanding where on that spectrum are we. Are we on the certainty? And I can, for example, the separation of the forebody of the shuttle where the crew sat with the
Mm-hmm.
pressurized volume. We know exactly to the millisecond when that happened because we have a data recorder that lost power, and that data recorder was recovered in the field, and we could tell exactly when it lost power. On the other end of the spectrum, the the debris that was recovered in the field, some may say indicated that an event happened in a certain manner.
Mm.
Well, that's possible, but that data could also explain it in a completely different manner. So my job was to keep the team focused on saying, where on that spectrum are we? Because if you made the wrong decision or drew the wrong conclusion, that had very big consequences in terms of how we're going to fix this.
Right.
So an example, just to give you one,
Yeah.
debris that was recovered in the field. It varied from the massive power heads of the main engines, the three main engines that the shuttle had, which of course were completely idle during entry because they're only used on ascent. But these are multiple hundreds of pounds of solid steel, solid material, versus a piece of aluminum structure from the inside of the space shuttle, which was again recovered in the field, but was recovered in a manner that would suggest a directional heating during the breakup of the shuttle. But if you looked at a piece of debris that was actually right next to it, it was completely pristine. So if you were to draw your conclusions based upon the piece of pristine material versus this piece that was completely thermally eroded away, your conclusions would be completely erroneous. And
Mm.
therefore, if you were trying to decide how do we fix the vehicle to improve crew survivability, you may be going down the wrong rabbit hole very quickly. So, as a team leader, as a project manager, my job was to keep the team very focused on where are we on that spectrum.
So this is really close to the core of what I wanted to grapple with you is this idea of you called it going down the rabbit hole, or maybe you could think of it as adopting a theory or a hypothesis or a scenario, and both in the context of this particular investigation, but just in general as your experience as a scientist. I wanted to ask you your perspective on the way that we all as humans have a kind of innate tendency to take up an idea and cling to it. And it can be a little bit hard to let go and say, well, you know what, maybe that wasn't right.
Yeah, that's human nature, right?
Mm-hmm.
We tend to believe in one thing and go after that and say that is absolute truth. The way I'm going to put it in retrospect, post the Columbia accident, right?
Mm-hmm.
we came up with a process which some people may call dissenting opinion. I abhor that term because the word opinion means, if you look at the definition of opinion, it says that it's not necessarily based upon facts.
Hmm.
Well, in my world, if you have an opinion not based upon facts, then all that is an opinion.
Maybe
If
more
you're
like an
going to come up with,
assessment.
I'm sorry?
More like an assessment. Like assessment might be a better word.
Well, we came up with the term formal dissent, right? Because
Okay.
it implied that the person who had the dissent had facts to back up their argument.
Okay.
So the formal dissent process, or the dissenting opinion process, which was the original term that was instigated post Columbia, became part of NASA's culture. So at team meetings, for example, or program manager meetings, now there was a requirement for the team, the chair of the meeting, to say, does anyone have a difference of opinion or a dissenting opinion to the decision we've just made? And that happened in all the way up the management chain, all the way to the flight readiness reviews that happened before every shuttle flight. So there was a call out there that does anybody believe that we haven't looked at all these facts in the right way? Have we made the wrong assumptions? And people did speak up. Um, um, it was very refreshing to see this now, sitting in these flight readiness reviews, to hear people say, you know what, I really don't think that's the right decision, or I think we could look at it a different way. So I think one thing the accident did serve, and I think that's true of any accident, is it forces one to open one's mind a little bit more to the possibilities that it may be a different explanation for what you're seeing.
That's an incredibly powerful idea. I think that there's such a strong tendency for people to get into a groupthink mentality, to just kind of go along, for social reasons, but also there have been some psychological experiments where people like actually just believe something because everyone else seems to believe it.
Yeah.
And that is a powerful force. And so to consciously implement a procedure that is designed to push back against that tendency, that's pretty cool.
It is pretty cool, but if you think about it, it's completely outside of what you'd think about NASA, right? Um,
Yeah.
you'd think that you'd have this person who's no be all and know all and end all,
Yeah.
sharing this meeting, that they know everything that there is to know about human spaceflight. Well, that's just wrong, right? I mean, they don't. They rely upon the cadre of senior engineers, senior scientists sitting around the table who have decades of experience amongst them, right? Hundreds of years of experience when you think about it, who have ideas that perhaps in the past they hadn't wanted to voice because they didn't want to appear to be the naysayer in the group. But just your comment about groupthink
Mm.
is has been very evident in NASA and it's very evident in the two major shuttle accidents we've had. Right, we called it because we didn't call it. Diane Vaughan coined the term the normalization of deviance. She was an author that wrote the book on the Challenger decision, the decision to launch the Challenger vehicle. This normalization of deviance, or groupthink, if you want to call it that, basically what it says is, you've seen all this before. Your mind says, we've seen this before. We understand it. We know it. We've seen it. It's not a problem. Press on. And that's exactly what happened in Columbia, by the way. As I mentioned, we had seen foam shedding from the external tank on every single flight before Columbia, and it had hit the bottom side of the orbiter where the tile is, and we saw that every flight. In fact, the crews used to get out after the landing. They'd walk around the underside of the vehicle and they'd look at the tile, and they'd see gouges in the tile. And it turned out, okay, there was damage there. It didn't penetrate all the way through to the very sensitive metal that's underneath that tile during entry. So we replaced the tile and we flew. We reflew the vehicle. And so that became this normalization of deviance. So we saw the hit on the Columbia accident on 107, and most people said, okay, it's not a safety of flight issue, it's a turnaround issue. It's going to take time to replace those tiles before we can turn Columbia around and fly again.
Right.
But it's not just NASA that is subject to this normalization of deviance. It happens in every industry. People in oil and gas facilities will say, well, that valve over there, it's always been working like that. It's always had a pressure spike. When we open it, it's not a problem. The pressure will work itself out until one day, of course, that pressure goes too high and you result in an accident that kills people.
It happens all the time in aviation accidents. I just
Absolutely.
finished writing up a report on a accident that happened last year where they were supposed to stay within these boundaries and they exceeded it, and they'd exceeded it before and it hadn't been a problem. Yeah, really, really common phenomenon.
Yep.
I wanted to run something else by you. To assess risk, you have to have a model of the system and also an understanding of where your uncertainties about that understanding, where they lie. Okay. And so if you have good understanding, you can predict outcomes with a pretty high degree of reliability. And if not, your predictions will pretty much fail. And I was wondering if you think that the engineers and managers of the Columbia were to a certain extent surprised by the behavior of their systems because their model was bad. And this gets really to what we were just talking about.
Sure. Let me address the model driving reliability and probability of failure, for example. I'm going to give you an example that may surprise some people, but so the very first shuttle flight flew in 1981, STS-1, commanded by John Young, who had walked on the moon the decade before. Bob Crippen was his pilot. We had had no test flights of a shuttle, right? So the first flight of a shuttle was a crewed flight. The estimates of losing that crew in terms of the risk inherent in human spaceflight, the estimates at the time of losing that crew was somewhere between 1 in 1,000 to 1 in 10,000. And that was based upon the data that we had available at the time, reliability engineering, that type of tool. So the data and all the tools told us that was roughly the range we were talking about. And you compare that to, estimates of being struck by lightning of, 1 in a million, 1 in 10 million, whatever. So let's now go to the end of the Space Shuttle program in 2011, 135 flights, 2 major accidents with 14 fatalities. We now have all that data, and now we have very modern tools to evaluate risk. Right? And the tool that we used and we relied upon for a large portion of the shuttle program was what is called probabilistic risk assessment, or probabilistic risk analysis, PRA. So we applied all of that data that we had generated in 135 flights, and using this modern tool, we were able to go back and look at the real risk of that very first shuttle flight back in 1981. And it wasn't somewhere between 1 in 1,000 and 1 in 10,000. It was actually 1 in 12. So it just goes to show you that your understanding of risk depends upon the data that you have available at hand and the tools that you have available to analyze that data. So we use this probabilistic risk assessment tool for every flight post Columbia to say what is the overall risk of losing the crew on this flight. And of course, the shuttle was a hugely complex system. We have models of every single component. and as a system overall, we could generate what this probabilistic risk assessment tool number, and it ended up that we set a threshold, and we said if that threshold goes below 1 in 200, and remember in risk terms, a lower number means a higher risk.
Mm-hmm.
So if it goes below 1 in 200, then the program manager needs to seek higher authority to fly that flight. It doesn't mean we can't fly it. It just means that we want to have that risk accepted by, for example, instead of the program manager, the associate administrator for human spaceflight. Or if it gets higher risk than that, all the way up to the NASA administrator.
Right.
And in fact, there was one flight. It was the final servicing mission for the Hubble Space Telescope. That risk was significantly higher than that threshold. And that went up to the NASA administrator. And in fact, just to bring in what we talked about before about dissenting opinions,
Mm-hmm.
there was a dissenting opinion that said we think this flight is too risky.
Mm.
And the reason being is because Hubble was at such a high altitude that the debris field at that altitude was a higher risk than, for example, a normal space station flight.
Got it.
So the dissenting opinion said we think spending that amount of time at that high altitude servicing the Hubble Space Telescope is too risky.
That's really interesting. I mean, I think there's a part of science that is very almost antithetical to human nature, which is the the necessity of accepting ideas that are possible, but that you don't actually believe 100%. And the idea of Bayesian inference is something that I became familiar with because of MH370. And it's basically this idea that you have various possibilities that exist. And instead of clinging to them and saying, I believe this or I believe that, say, I understand that this is possible, A is possible, B is also possible. And as more information comes in, I will adjust the relative probabilities. And I think this is what I was getting at with this idea of like you have a model, you expect something to happen. If that expectation isn't fulfilled, you change the probability. Don't necessarily throw it out. But as you're saying, okay, well, what if the mission has this parameter? Maybe it has a higher altitude, So as we have these different aspects, we're going to change the probability. And what happens where it really comes a cropper is if the model is maybe proven wrong is too strong a word, but if evidence comes in that is counter to the likelihood of that scenario being correct, failing to adjust, failing to say, okay, we now have to think that this is less likely. If you believe in a black and white world where it's this has to be true or it has to be false, then you can't really update your probabilities.
That's true. And you've hit, you hit the nail on the head, really, Jeff. And that is that, but you have to be driven by data, right? I mean, that's the true nature of this beast, is that it is fed by data. So, and data is real, and you can't say it's wrong because it's right there in front of you. We have data from sensors, and which have, yes, their own variability and their own limits in terms of precision. But I'm going to give you a very recent example, which is in the news even today, right?
Mm-hmm.
So NASA made the decision to bring Crew 11, 4 of the crew members that were on the space station, home because of a medical issue with one of the crew members of that crew of 4. We have modeled the possibilities of having to bring a crew home because of a medical event. The probabilistic risk analysis has medical event as one of the risk lines, right? And that PRA had told us that we've been flying the space station now with people for 25 years. The PRA told us we would have had 3 medical events in that time frame that would have brought a crew home. Well, it didn't happen until this particular case, right? And thankfully, I just looked at the news this morning. They splashed down off the coast of the Pacific. off the coast of California this morning, and everyone got out of the vehicle fine. And so now that medical condition is now being addressed by the finest minds that are out there. But the prediction that we had before would have said, you know what, we would have had 3 events in that 25 years that we would have brought the crew home. Well, we only have had 1. Now, we'll tell you there was another one that was close.
Oh, really?
But that's not a bad prediction when you think about it, right?
Yeah.
We tend to err on the side of conservatism.
Well, when you're dealing with human lives, I think that's probably the way to go.
Yep.
I wanted to actually dig a little bit into something you said where it's all data. And I actually want to say that in talking about some of these cases, I find it really useful to talk to people who have a kind of gut level knowledge of things. For instance, with MH370, I talked to a lot of 777 pilots because there's a lot of strange things about this case. They seem strange to me. And I say to them, does this seem odd to you? Does this kind of put the hair on the back of your neck up? And you, as you were saying, we started out by saying that you were dealing with people who had expertise in a lot of different fields. And so something that might seem not that unusual or doesn't seem that strange to somebody with one field of expertise, somebody else who's really studies that area might say, I've never seen this before. This feels odd.
Yeah. It doesn't even have to, I'll be honest with you, I've had many of those feelings sitting in flight readiness reviews or safety and mission success reviews. I sit there and I listen to the presenter talking about something, and I'm just thinking in my mind, this is not right.
I think it's called a bullshit detector.
Well, it's not even a bullshit detector because the person truly believes what they're telling me is correct, right? And in fact, the data will tell you what he's saying is, or she is saying, is absolutely right. But still, part of you is going, you know what? This just doesn't seem right. And I've had those feelings on multiple occasions. Thankfully, whether it's, and I'm sure it's because of great engineers, but also some might say we got lucky, right? In some cases, we did. Sometimes those hairs going on the back of your neck are a very good indicator that you need to start asking a few more questions. And I will tell you, people will tell you if you ask what Nigel Packham's what they might think of me after I've retired now, they might say he asked so many damn questions, and he wanted to know so much about a certain flight when there really was no issue. And I'll admit I will certainly put my hand up and say that's me. But when you were flying 7 of my friends on a vehicle that has the capability to blow them up in an instant, I care about them. And I'm sorry, but just, humor me, answer my questions, make me feel a little bit better because I don't feel quite right at this point in time. And I think we need, I value people that ask those questions.
I think it also really points. Sorry,
you may be called a pain in the ass because you're asking them, but I'm glad I asked them, and I'm glad I got to the bottom of some of these concerns because sometimes they said, we hadn't thought about that.
But I think it really speaks to the importance of expertise, of time in a field, which cannot be replaced by Chat GPT or anything else. You can't just do a Google search and get that kind of that hair on the back of your neck standing up kind of thing. I do feel that. I do feel a bit of horror at the prospect of losing expertise because people can just get it automated. I think we need to have people really understanding these systems.
Well, you're going to get to the question perhaps of artificial intelligence and how that plays into decision making. I think AI is a great tool, but is a tool, right? And just as probabilistic risk assessment, by the way, is a tool, that's all it is.
Yeah.
And it's a tool that is fed data and spits out a number. But there's a lot more involved in what does that data really mean? Just as AI, I think, as I say, is a great tool, but use it in the way it's supposed to be used, which is to guide you perhaps into asking certain questions. But to blindly say, okay, AI, what's the likelihood of me losing my crew on this flight? And it tells you it's 1 in a million. I think I would be asking a few more questions.
So I've been asking you about kind of the big picture, kind of this sort of abstract ideas about accident investigation, but the accident we're talking about here is an absolutely unbelievable and fascinating case, tragic, impactful, historic. And I think I'd be remiss to not actually ask you a little bit about what happened and what your work was and what you concluded and the impact that it had. We talked about the vehicle re-entering, the structural failure. You were looking at what these human beings experienced, and I think some of the questions were, well, what did they experience before they lost consciousness? And I don't want to get too much into the gory details, but I would like to know what they experienced and what happened to them.
Well, the first thing that happened upon entry, because of this hole in the left wing, is it became very unstable as it entered the Earth's atmosphere. And because of this, the hole created a lot of drag on the left wing, which tended to try and turn the vehicle around. The vehicle, which is flying autonomously, by the way, the crew is not flying the shuttle. The vehicle tried to compensate for that excess drag, and it held on until the bitter end. Until it
held on how? By thrusters or flight surface deflection?
So there are thrusters on multiple places on the vehicle, but the ones in question that were important on that day were the aft thrusters on the left side. So as the vehicle was being pulled around because of this hole on the left wing, thrusters on the aft left-hand side were firing continuously. So they were trying to compensate, and the vehicle was also banked a little bit more extremely to try and compensate. Now, those thrusters, as I say, normally fire anyway, but now they were firing, all 4 of them, continuously, basically hanging on with the fingernails to control. But it finally gave up the ghost. It could not overcome this excess drag, and it went into what we call loss of control. At the end of this loss of control period, the front part of the shuttle actually separated from the rest of the vehicle. So now we have this free-flying entity called the forebody, which is where the 7 crew members are in their pressurized volume. But as this separation happened, the pressurized container shifted inside this forebody and created a hole in the bottom of the pressurized module. Now, a hole in a pressurized module is never a good thing, right? Because it's still in the vacuum of space, as it were. So now all the air that was inside the vehicle started to leave. So what happened was the cabin depressurized, just as it does in airplane accidents, for example, which is when the oxygen masks drop and the cabin crew or the pilots will try and reduce the altitude to get to a place where it's a breathable atmosphere outside. Well, unfortunately, in the case of Columbia and space shuttles, we're at 200,000 feet. So the ability to dive down to a lower altitude is absolutely not there. But the air inside the pressurized module left very quickly. So the astronauts inside the crew module suffered from what's called hypoxia, and they lost consciousness between 6 and 8 seconds after the initiation of cabin depressurization. Now, it was not an explosive decompression. Explosive decompressions happen even in aircraft accidents, But this was not explosive, but it was a very rapid decompression. So they were unconscious within about 6 to 8 seconds.
Mm.
There's a term used in aviation called time of useful consciousness, which the crew is still conscious, but because of the lack of oxygen going to their brain, useful consciousness in terms of their ability to actually do things that make sense
Mm.
was even less than 6 to 8 seconds. It was probably on the order of 2 to 3 seconds.
So, for instance, they weren't able to lower their visors or
Yeah.
react to respond to the
So
depressurization.
so you refer to visors because the crew were wearing full pressure suits,
Mm-hmm.
and they had been after the Challenger accident. Every flight after the Challenger accident, they were wearing full pressure suits. But the pressure suit has a helmet, which has a visor, which is normally up.
Mm.
Only in the event of three events would they go visor down. One is a fire, one is a toxic atmosphere, so if they smell something in the cabin, they would go visor down, or a cabin depressurization. But it happened so quickly that none of the crew went visor down
Mm.
and initiated their oxygen flow. You could say it's because of the very rapid depressurization event, but also it could well be that, as I mentioned, the full body lost power, so it had gone completely dark,
Mm.
right, except for the chem lights that the crew had on their pressure suits in case of crew rescue.
These are like bioluminescent
But
strips,
they use just chem strips. So if you go
chem strips,
diving, if you do night
not
diving, for
bioluminescent,
example,
just like yeah,
yep,
like you
there's
wave
one
at
on
a
each
at a
shoulder.
festival. Yeah.
Exactly. There's one on each shoulder.
Mm-hmm.
And they had lost communications. Right? So they couldn't talk to each other. They probably couldn't see each other very well. And the vehicle had been moving around before this event had happened.
Mm.
So even though it probably wasn't injury inducing this movement,
Mm.
it was probably very disorientating because this was the first G force that they'd seen in 16 days.
Mm.
So we will never know why none of the crew went visor down,
Right.
but none of them did. So they did endure a lack of a loss of consciousness after 8 seconds, and they never regained consciousness. Right? So
Yeah.
the important thing to note is that everything that happened after that, the crew was completely unaware of.
Right.
Right?
Mercifully, because in your report you have a list of all of the things that would be fatal to the human body,
Right.
and there was
We,
many of them. I mean, this was multiply non-survivable.
Correct. So we identified, and this is what a crew survival analysis does, right?
Mm-hmm.
We identified 5 potentially lethal events to
Mm-hmm.
which the crew was exposed. Cabin depressurization, loss of consciousness was one of them, and they go through the gamut of a very rapidly rotating environment. The crew is in a non-conformal space helmet, so
Mm.
now an unconscious crew. Of course, there's no way to protect the head inside the
Okay.
helmet. Eventually, the crew module broke apart, and the crew was extracted from their seats, and there's interactions with the remainder of the debris field.
Mm.
High temperatures, and then at lower altitudes, low temperatures, and then of course impact with the ground.
Mm.
So those 5 lethal events which we identified, Columbia was exposed to all 5 of them. But our job as survivability individual experts, if you want to call us
Mm.
that, was to look at each of those in turn and to say, was, for example, that cabin depressurization survivable on its own?
Right.
And the answer was absolutely, right?
Mm.
They wore pressure suits. Had they been visor down, oxygen was flowing, that particular event, the cabin depressurization, was absolutely survivable. As was ground impact when you think about it, because they have parachutes. But that particular event on its own was survivable had the parachutes functioned, had they been conscious to be able to get out of the vehicle and the parachutes opening. But on its own, that ground impact was completely survivable from that one event.
Mm-hmm.
So, of the 5 potentially lethal events that the Columbia crew was exposed to, 3 of them were absolutely survivable.
Mm.
One was not, and one, because of the limitations on the testing we had done on the pressure suits, was questionable.
Mm.
Um, and that's the job that my team had to do, right? Which was to investigate the survivability, look at what could be improved in order to allow the crew to survive an accident in a future accident.
I think it's really fascinating that you guys went into such granular detail on an event where I think a lot of people would look at it and say, well, of course you're not going to survive that. There's nothing survivable about it. Your spaceship broke up on reentry. And I think that that's really what good science is about. It's about putting aside the temptation to indulge your assumptions and say, well, how confident am I about these assumptions? Assumptions are such a killer of understanding.
Right. Yeah, absolutely. I mean, there are people, for example, that said, well, you could have built a system that would have protected individual crew members in the event of an accident like Columbia, like a
Mm.
little cocoon that came over the head of each,
Yeah.
encapsulated each crew
Yeah.
member that had its own oxygen supply, its own parachutes, its own survivability equipment. Sure, absolutely. You never get it off the ground.
Right.
Or because of the absolute mass of those cocoons, the capability of the rest of the mission would have been minimal, right?
Yeah.
There are other people who would say, well, why didn't it go to the space station and hang out on the space station
Mm.
for a safe haven? Well, that couldn't have happened physically because of the inclination and the altitude that Columbia was at,
Right.
which drives another question. And these questions come up in every talk that I give about Columbia.
Sure.
And I've given this talk now hundreds of times. The audience, we've estimated the audience is now over 110,000 people that have heard this.
Wow.
People say, well, why do you even bother? Nothing,
Mm.
you couldn't have done anything about it anyway. My answer to that is normally a very crude word.
Sure.
But I said, we're NASA, right? If we had known on flight day 2 that there was a hole big enough in the left wing that the vehicle couldn't have survived, we would have done everything we possibly could have done to get another shuttle up there and attempt a rescue.
Mm-hmm.
Now, would it have been successful? I have no idea,
Yeah.
but I can guarantee you would have tried.
There's a very famous story. I forget who told it, but there was the idea that the moon lander had a single point of failure, vulnerability, it only had one engine to take
Yep,
off with, and that if that had failed, there was nothing that the astronauts on the ground could have done, but that they would have died trying to do something.
absolutely. And by the way, there were multiple single point failures on the lunar module,
Okay.
as there are in the space shuttle, right? But we as there were in the space shuttle, but we pick our systems very carefully, and we pick redundancy very carefully. If they are systems, and I will tell you that the commercial space industry has heard that. They
Mm.
understand it, and for systems that will create what we call a catastrophic hazard that could lead to loss of crew, NASA requires redundant systems, right? We call it
Mm-hmm.
failure tolerance, to be able to take a hit and keep going. And commercial space has heard that, and they say,
Mm-hmm.
you know what? Yeah, we understand that if a system is so critical that if you lose it, that you're going to kill the crew, then we need to build some failure tolerance into that system. And
Yeah.
they're doing that. They understand that.
I wanted
We
to.
will
I
still
wanted to.
have systems on space vehicles that don't have redundancy to their function. but like the likelihood that they would create a catastrophic hazard and kill the crew is very, very small.
Got it. I wanted to clarify something when we were talking about what the crew of Columbia experienced. The thing was already breaking apart when they suffered that depressurization that was fatal. The thing had, so when we see this footage of the debris streaking across the sky, that had already started to happen. The crew was still alive and functioning as it was coming apart.
Correct. And in fact, because the crew simulates entry, descent, and landing multiple times, the very first motion of the orbiter, as soon as that motion had happened, the crew would have known we're not going to make it home.
Oh my God. And how long did that process last?
The loss of control before the vehicle started breakup was on the order of several seconds.
Oh, really?
Going from a vehicle that was still in control to being a vehicle that was out of control with its belly into the wind was about 10 seconds or so.
Okay. And then from that point till the depressurization, how long was that?
I'd have to go back in the timeline, Jeff, but it was on the whole event took on the order of less than a few minutes.
Okay. Okay.
But what ended up happening, of course, now is that you have, and I'm going to draw a parallel with aircraft accident investigation. Don't forget the debris footprint of the Columbia accident was 400 miles long and 10 miles wide.
Incredible.
There aren't too many airplane and accident investigations that have to deal with that type of footprint. TWA 800 was on climb out, obviously. Lockerbie, maybe Pan Am, had a larger footprint than that, but not that much. But 400 miles long, 10 miles wide, so 4,000 square miles to have to search. It's not a rescue mission, obviously, but a recovery mission and debris search with 25,000 people in the field, largest ever recovery investigation ever done in the United States and probably in the world.
It was incredible. I mean, the amount of energy that was involved in that accident, I think unprecedented. Well, maybe in other space things, but I mean, many orders of magnitude amounts of energy compared to, I mean, Mach 15 or something versus, 600 miles an hour or something.
Breakup started around Mach 18.
Okay, so this is an absolutely tremendous amount of energy.
Absolutely. Don't forget the thing about space is it takes a huge amount of energy to get up there, but that energy has to be lost somehow when you come back in, and that's through frictional heating going through the atmosphere, and the vehicle actually ends up doing a lot of S-turns to lose that energy. But at 200,000 feet altitude, it still hadn't lost a lot of that energy, so there's still a huge amount of energy involved.
So the final part of your role is to make recommendations for what we can do to prevent such a thing from happening again. I wanted to ask you about what were some of and spaceflight changed, at least for the United States, very dramatically. There was a long pause in our ability to put people into space. And when it was regained, it looked very different. What were some of the ramifications of the work that you did?
So the major ramification in terms of a shuttle program itself, let me address that one first, because that became important.
Yeah.
We now instigated what was called CSCS, launch on need. Now, I can't remember what CSCS is, crew survivability, crew rescue, if you want to call it that. But essentially what it meant was before every shuttle flight took off, we had an understanding of how long it would take to launch another shuttle to go get it, to go get the crew. And don't forget, after Columbia, every flight after that, apart from Hubble Space Telescope servicing mission number 5, went to the space station. So the safe haven capability was there. So we did an analysis before every shuttle mission that said, how long would it take if we discovered a problem that meant that shuttle couldn't come home? how long would it take to launch another shuttle to get up there and bring that crew home? So that apart from the very last shuttle flight, we always had that capability, right? So that was a major development from the space shuttle program itself. From the survivability perspective, we had about 29 recommendations that came out of our report. And our report is 440 odd pages long. It's highly technical. As project manager, I understand about 10% of it, but I'm not supposed to understand everything in there. That's why I had the people I did on the team. But of those recommendations, all of them applied to the shuttle program, which of course is a winged vehicle. Right? A lot of the new programs that came out after shuttle program ended are now for exploration, for example, for Artemis, capsule based. And so a lot of those recommendations didn't apply to a capsule based environment, but a lot of them did. Like, for example, head and neck protection. So the new programs, Orion, the Orion spacecraft that is about to leave in February this year to go around the moon, the crew will have adequate head and neck protection. For the shuttle program itself, our recommendations were varied, and the program manager came to me and said, "Nigel, listen, you got a lot of recommendations there. Which ones would you suggest are the highest priority? Put them in priority for us so that we can address them on the basis of how much money we have and how quickly we can get them integrated into the shuttle program." Because unfortunately, it takes a long time to make a change, as it does in any aerospace environment, by the way. Takes a long time and a lot of money to make a major change in a spacecraft, and that's certainly true of a space shuttle.
Yeah.
The first recommendation we gave them was to change the straps that the crews strap into their seat. One of the findings, and which is linked to one of the potentially lethal events, was that the crew was not strapped into their seat by the acceleration. So just like you and I have a seatbelt in your car or truck, if you slam the brakes on, you know that inertial reel will lock, so it stops you from going through into the windshield. Same thing on the space shuttle. But because of the design of the inertial reels that we had on the seats in the shuttle, those did not lock. So now we have an unconscious crew with an unlocked inertial reel set of straps. So now a lot of the injuries that were created were because of an unrestrained crew.
Yeah. I mean, that's a great example of a really famous slogan in air accident investigation or just aviation in general, which is that the rules are written in blood.
That's
These
true.
people died, but we can change it. We can make the system better because they died, we can change the rules. And I think that kind of institutional memory is easy to overlook, but we live in a world that's safe right now because of the kind of meticulous attention to detail and the amount of really money, human effort that's been put into examining things like this. And so earlier I was saying, a lot of people might say, well, why even look into it? Of course they're not going to survive. But when you've learned things that can be applied later. I wanted to circle back to another idea that we had hit upon earlier, this idea that if they knew that this problem existed, they would do everything in their power to make sure that they did what they could. And I think one of the frustrations with MH370 is that the mystery hasn't been solved, and yet the investigation has been put on ice. And there's a sense of people, of which I frankly share, that you have not done everything in your power. You've left it hanging, and there should be more to be done. I don't know how familiar you are with that particular case, but I wanted to ask if there was any advice that you would have if an inquiry were to be restarted. Would you have any advice to offer?
I would say keep going until you fully understand what happened. You know, the 7 crew members on board Columbia, Rick Husband was the commander, all the way down to Ilan Ramon, who was the payload specialist out of the Israeli Air Force.
Mm-hmm.
I can give you every single name, and I can tell you exactly what rank they had in what military branch. They were not just crew members; they were very good friends of mine. I was a test subject for that crew for multiple years, so I had people. I still remember Willie McCool, was it Dave Brown, drawing blood from me. And after he had drawn that blood, he passed that vial over to Mike Anderson, who was the payload commander. This is on the ground, of course.
Mm-hmm.
And Mike dropped the vial of blood, and it shattered on the floor.
Mm.
And I went over and put my hand on Mike Anderson's shoulder, and I said, Mike, don't worry. Next time you drop something like that, it's not going to drop.
Wow.
So I give you that story only because to tell you that these people were very good friends of mine. So investigating how they died and how I can make things more survivable for their friends in the future was what kept us going, right?
That's a great lesson. That's really a great lesson. I think that if I could underscore anything that I've taken from what you've shared today, which was so invaluable, I really appreciate it. It's that we just have to keep on going. We cannot just shrug and say, well, we've done our best, because we haven't done our best. We are capable of solving these mysteries. We're capable of digging in and really exerting ourselves. So I think that's a really inspirational note to stop on. But Dr. Packham, I want to thank you so much for taking the time to talk with me today and to share everything.
Jeff, you're so welcome. And it's as I said, I will talk to anybody, anywhere, at any time about Columbia, because it is something that is very, very clear, very, very dear to my heart.
Wonderful. Thank you so much.
You're very welcome.